In this video, we will explore the ability of spheres of the same size to group together in a most effective minimum arrangement. This is called the closest packed state, meaning the centers are as close together as possible and each sphere is touching as many other spheres as possible. We learned that 4 circles can self-organize into both a sphere and a 14-sided vector equilibrium. Here we see 146 spheres closest packed and 3 layers around our central U-Me ball can also construct the VE. Let's begin with what we know. To measure distance with spheres, you always measure center to center. For example, 4 spheres in a row measure 6 BB equals 12 centimeters, with BB always being 2 centimeters. We learned that spheres can closest pack around our U-Me ball on the same plane as our level playing field. This defines an all-purpose hexagonal equator for any structural order that radiates out from the center. Pictured here are the different sized VEs that define the layering around our U-Me ball. These 3 layers grow out of the work of Buckminster Fuller. I base my explorations on Fuller's theory of the closest packing of same-sized spheres because it's based on the triangle, the only self-stabilizing shape found in nature. His theory begins by asking what is the minimum number of spheres necessary to construct a most effective minimum closest packed layer around our central U-Me ball. The answer will always be 12 spheres with a distance of 2 BB equals 4 centimeters between centers. These 12 spheres around one define the 50-direction communication network that connects the center to all of the fundamental locations in common on the outside limit of the 6 BB VE. The closest packed state of spheres is one of the most fundamental structural and numerical constants found in nature. I am told that it is the basis of crystallography and atomic structuring, but I don't know anything about these subjects. Let's just say closest packed spheres reveal a great deal of useful information if you want to improve the structural integrity of your building designs. Here is Fuller's theory in one image with a 4-circle model of the different sizes. We start with our BB radius U-Me ball. There are 12 spheres around the one in the first layer, 2 BB radius. The second layer needs 42 spheres around the 12 and around the 1 with a radius of influence of 4 BB equals 8 centimeters. The third outside layer has 92 spheres around 42, around 12, around 1, defining a 6 BB sphere of influence. I define this as the first cycle of initial growth of fundamental structure. All other structures will be relative to this limit. I have shown you how circles, triangles, and spheres can self-organize to build a solid push-off start to your exploration of structures. In the next video, I will introduce the outside containment field surrounding all that we have built so far, the 12-sided rhombic dodecahedron. It has all the properties of a sphere, but gives you 12 flat surfaces to work with. The R dodecahedron is built using 12 sphere diamonds. This introduces our third basic structural constant. The color green gives you this information.